Well, today at least we have a whiteboard. So in case the technology does not work, we can still use the whiteboard. Okay. So let me remind you of what we have done so far. Okay. After speaking about the properties of charges, we said the charge is conserved. If you have an isolated system, the charge is conserved. We mentioned that the charge is quantized, so the charges occur in multiples of E, can be positive or negative. Same sign charges will repel each other, and opposite sign charges will attract each other. And Coulomb performed an experiment where he was able to determine the magnitude of the force between the two charges, and we said it's equal to K, Q1, Q2 divided by R squared. So here we did the absolute values because we are interested in the magnitude. Once we determine the magnitude, we use our reasoning in order to determine the direction. So once we determine the magnitude, we can write the force vector in unit vector notation as a function of I, J, and the K vectors, unit vectors. And last time we defined the electric field. We said if you have a charge in space, it will create an electric field around it. Okay, and in order to measure this electric field, we bring a positive test charge and we put it in the proximity of this charge and we measure the force. And if we divide the force by the charge, the test charge, we will get the magnitude of the electric field. And we said the electric field is always pointing away from a positive charge. The electric field is always pointing away from the positive charge and towards a negative charge. So if the charge is positive, like in this case, the electric field is away. But if the charge is negative, the electric field will be pointing towards it, like this. And obviously, we can determine the magnitude of the electric field. So this is the magnitude of the electric field. It's the Coulomb's constant times the test charge Q divided by the distance R squared. So you can see if we get close to the charge, the electric field is quite high. And if we get away from the charge, the magnitude of the electric field decreases as 1 over R squared. Okay? So how do we represent the magnitude of the electric field? Usually we use what we call the electric field lines. We can use electric field lines to determine not only the magnitude but also the direction of the electric field. So let me go to the presentation mode. Okay, so let's go to the next. Michael Faraday, who is a British scientist who lived in the early 1800s, introduced the concept of electric field and a way to represent them. And so the way he represented electric field, he used what we call electric field lines to help. So, for example, let's assume you have an electric field, and now the green arrows are showing the electric field vectors. So what you can do, you can draw the electric field lines. The electric field lines are tangent to the electric field, or the opposite. We can say the electric field vector is always tangent to the electric field line. Okay, so and we always indicate the direction of the electric field lines in the same direction as the electric field vector. So for example here, if I were to draw the electric field, so if I draw the electric field here, so this is the electric field here, the electric field vector, and so on. So here it will be tangent, so this is the electric field vector, and so on. So these are, so first of all, they indicate to us the direction, okay, but also we can use them to indicate the intensity. And the way we do that is, okay, so first of all, usually electric field lines, they never cross. They will never cross, because if you have an electric field line, two lines crossing each other, as if you're saying at this point here, we have the electric field like this and the electric field like this, and it cannot be. There is only one electric field vector, and so this is how we represent it. Okay, Can you please pass the attendance sheet? Thank you. Okay, so the electric field lines, they do not cross. They can converge at the same charge. For example, if we will see that if you have a positive charge and a negative charge, the electric field lines, they will go away from the positive towards the negative. So they can converge at a point charge, for example, but they cannot cross each other. Okay? The next thing we can do, we can use the density of the electric field or the intensity of the electric field by using the number of lines. So here, for example, we have an imaginary area, unit area, and we are showing the electric field lines. To the left, we have many electric field lines crossing the area, but to the right, we have only few electric field. So this indicates that we have a strong electric field in this region. So this is a strong electric field here, and we have a weak electric field in this region. So not only can we indicate the direction of the electric field using the drawing of the electric field lines, we can also somehow indicate the intensity of the electric field. So the number of lines per unit area in a plane perpendicular to the electric field lines is proportional to the magnitude of the electric field. So meaning the number of lines per unit area is proportional to the intensity of the electric field. So this is what we are trying to indicate here. All right, so let's look at a couple of examples. So here is, for example, a positive charge. The positive charge, we said the electric field is always, if you bring a test charge, Q0, a positive test charge, we can measure the force actually. So this is the force. The electric field is pointing in the same direction as the force on the positive test charge. So this is the electric field. But if you bring the test charge here, the electric field will be always radial. So any point. So these are the electric field lines. So first of all, they are in the same direction as the electric field at any point. So if you draw the electric field at any point, these are the and the other thing, notice here, as you get closer to the charge, the radius of this sphere gets smaller, the number of lines per unit area increases. So we can see, for example, let's say this is R1, and let's assume this is R. You can see that the number of lines per unit area of the sphere is equal n divided by the 4 pi r squared. Okay, so as the radius gets smaller, this number, we said this is proportional to the magnitude of the electric field line. As r gets smaller, the denominator gets smaller, the number gets larger. So the strength of the electric field varies as 1 over r squared. We have seen that before. Okay, this is just confirming the same concept. So the electric field from a point charge is stronger at closer distance to the point charge, because we know we can write E is the K Q divided by r squared. So we can see that the number of electric field lines n per unit area on the sphere of radius r is n divided by 4 pi r squared, because 4 pi r squared is the area of the sphere. Hence, E varies as 1 over r squared. This is what we call the inverse square law. This is very common in physics, in biology, and so on. Many things, if you measure them, they go as 1 over r squared. For example, the gravitational force between the sun and the planets that are around it varies as 1 over r squared. So the gravitational force, F, we said, is gravitational constant times the mass of the sun, mass of the planet, divided by r squared, the distance between them. So if a planet is closer to the sun, it will experience much stronger gravitational force. If it's away from the sun, it experiences much weaker gravitational force. Same thing for the charges. Okay, if a test charge is brought close to the source charge, it will experience a much stronger electric field, and vice versa. Okay, so let's show. So this is for a positive charge For a negative charge, it will be just the opposite. The electric field lines are pointing towards the negative charge, because the electric fields are also pointing towards the negative charge. So if we draw the electric field at any point, these are the electric fields. All right? Same thing if we draw a sphere here, same thing. We observe that the number of lines per unit area increases as the radius of the sphere gets smaller and smaller. Can you hear me well over there? You hear me? Okay, because I'm wearing a mask, and so if you cannot hear well, you can come closer to this side. Okay, so here we are showing a positive test charge. It will experience a force of attraction to the negative charge. So if we draw the electric force, it will be in this direction, and the electric field is in the same direction because the test charge is positive in this case. Okay, so the electric field lines extend away from a positive charge where they originate and towards a negative charge where they terminate. This is a general rule. Like we said, the electric field always pointing away from a positive charge and towards a negative charge. Same thing, electric field lines point away from a positive charge and point towards a negative charge. Okay, so here is an example. We have a positive charge and a negative charge. Okay, and we are drawing the electric field lines. As you can see, the first thing, the lines are pointing away from the positive charge and they are pointing towards the negative charge. Okay, the other thing you can see, if I draw a sphere here or here, you can see the number of lines is much more per unit area, is much more as you get closer to the charge. So if I draw another sphere like this, you can see the number of lines, the number of lines per unit area as the radius gets larger, it gets smaller. So this is very useful because if you draw the electric field lines, if you ask me at any point to draw the electric field, I can draw it because I know, for example, at this point, the electric field is like this. At this point, the electric field is like this, and so on. I don't know if you have an experiment where you draw the electric field lines in the lab. This is a very nice experiment, but you can do it in simulation also. Okay? All right, so one thing we observe, okay, or these are the rules of drawing electric field lines. Okay, the first rule, the line must begin at on a positive charge and terminate on a negative charge. First rule. Okay. In case of excess of one type of charges, some lines will begin or end at infinity, as we will see in the next slide. So if you have an imbalance of charges, not all the points leaving one charge will reach to the other one. Okay. The number of lines drawn leaving a positive charge or approaching a negative charge is proportional to the magnitude of the charges, or let's say it in a more accurate way. So the ratio of the number of lines in contact with the charges is equal to the ratio of the charges, or the absolute value of the ratio of the charges. So if let's count them, for example. Let's take this example and count. So let's look at, for example, the number of lines that are leaving the positive charge and are reaching the negative charges. And since the charges here are equal, they should be equal. So if we count, for example, let's count just the one leaving and entering leaving the positive charge and entering the negative charge. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We have 15 lines. Same thing, we have the 15 lines going into the negative charge. So if the charges are equal, so if Q2 is equal to Q1, then we have N2 is going to be equal to N1. So if we count also all of the lines, we will, if the charges are equal, the number of lines entering the negative charge and leaving the positive charge should be the same, because these are similar charges. Okay. Also, we said no two field lines, no electric field lines cross each other. You can see there is no crossing of the electric field lines, except they originate on a positive charge and they terminate on a negative charge. But sometimes they terminate or originate at infinity. Let's look at a simulation Thank you. Everybody signed? Huh? Yes, please. Okay. Now, I'm going to be flexible because I know some of you are taking courses in the other campus. Usually, I do not, if a student comes after 10% or 20% of the session, like for example, a 50-minute session, if a student comes after 10 minutes, I count him as absent. But because of this issue of registration and student taking courses here and there, I'm not going to do that. But please do not abuse of that. So come in time, because I'm trying so that you can discuss, we can interact with the explanation and so on. So if you really have an excuse, it's okay. But if you don't, then you should be absent. And if you come 15 minutes late, you should be absent. Okay? One of the students said that if it's possible, if we can advance this session to 11:35. To 11:35, because it looks like some students have a math lecture after this session. If there is no conflict for any of the students, it's okay with me. There is no conflict. Anybody has a conflict? You do. You do. If there is a conflict, I cannot. So, even if it's one student, because I would be, he signed up for this time spot, but if you have lectures before, a lecture after, you have the permission to come and leave. But please, try to at least follow the lecture or see the material outside the classroom, because you would be missing the explanations. Okay, so let's look at this simulation here. No, this one, not this one, this one. Okay, so this simulation allows us actually to place charges. So let's start up with a positive charge. Okay. So you can see the arrows are indicating the electric field line. So this is a positive charge. You can see the electric fields are pointing away from the, and I can draw electric field lines. Unfortunately, I cannot draw on Chrome. I cannot use my pen on Chrome, but I can take a snapshot and draw. But you can see the electric field lines. If, here I'm moving the positive charge. All right, so let's take a positive charge away and replace it with a negative charge. Okay, so if we place a negative charge instead, you can see now the electric field lines are pointing towards the negative charge, and you can see the direction of the electric field lines. If you draw a line, you can see that. All right, so let's put a negative and a positive charge. So let's bring this one here, and let me bring this one here. Okay. So now you can see that the electric fields are leaving or away, pointing away from the positive charge and towards the negative charge. Thank you. Okay, and unfortunately I cannot draw them, but you can see their shape. So they, as we have seen in the previous graph. Now, if I increase the charges in the positive direction, on the positive charges, sorry, so you can see I'm starting to affect the electric field lines, and so on. So you can see the more I put positive charges, I am affecting the, and if I draw the electric field lines, now the positive charge will have much more electric field lines leaving it than the negative charge, because now this charge here is 3 nanocoulombs. I put 3 charges, okay, and so on. Actually, this is a nice simulation because you can even measure the potential. We will see in the future lecture what is the potential. So you can measure the potential, and you can also draw the equipotential lines. Equipotential lines are the lines on which the electric field is constant. These are called equipotential. Equi means equal. Potential is the electric and also the voltage. These are lines on which the voltage is, or the electric field is constant. And we can draw them here. Let me start with only just the positive charge. Okay, so let me draw them. Okay, so here is, okay, this is one line, equipotential line. So if you go only on any point along this line, the electric field is going to be the same because it's the same distance from the charge. Okay, I'm going to draw another one. Okay, so here any point I move to. So notice that if I have a point charge, the equipotential lines are concentric on the charge. The equipotential lines are also perpendicular to the electric field lines. Did you notice this? You can see the electric field lines are radial, they are pointing away from the charge. The equipotential lines are perpendicular to the electric field lines. Okay, so this is an aside. Let's put another negative charge here. So let's put a negative charge, and you will see. So let's try to draw now the electric field lines. Let me put it just in the middle. All right, so here, okay, and so on. So you can see the electric field lines. Oh, here, do I have? Oh, I only need one charge. Yeah, so one positive and one negative charge. Let me put it here. Okay, so now I'm going to draw the equipotential lines. 1, 2, 3, 4. If I'm right in the middle, I should be able to get a straight line. Almost. Yeah, okay. So these are what we call the equipotential lines. These are the lines on which the electric field is constant, okay? And so it's a very nice piece of art, I guess. All right? Okay, so you can see. So we have electric field lines. They are used to indicate the direction of the electric field, and their density or their number per unit area indicates the strength of the electric field. The equipotential lines are lines on which the electric field is constant, and they are always perpendicular to the electric field lines. Okay, so this is a side, and obviously if I change the number of charges on one side, you will see that the equipotential lines will change significantly. All right, so let's go here. So here we're drawing, in this case, we have two positive charges, and they are equal charges, okay? And you can see the electric field lines are leaving the positive charge, but there is no negative charge. They are not converging on a negative charge. They are going away and on infinity, you can say. So we have, in this case, a positive charge Q here and a positive charge Q here. All right? If I have on the right case, I have a charge of 2Q on the left and minus Q on the right, and you can see the shape of the electric field lines is now skewed, and we have more electric field lines leaving the positive charge, double, than the negative charge. Let's count them. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16 lines here, and let's count how many are converging on the negative charge. We have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 lines. We said the number of lines, 16 divided by 8, should be equal to the charges. So we have 2Q divided by Q, which is 2. Okay? So this is how useful the electric field lines can be in order to illustrate, first of all, the direction of the electric field, but also the strength of the electric field. Okay, I want you to start the Kahoot and answer the following question. Okay, what is it? Okay, let me start. Save. And okay, and let's play. Basic mode. Okay, so please enter the pin. It will show shortly. Okay, so enter the pin, and while you're entering the pin, I will show you the question. Okay. So while you're joining, you will be able to still see the pin on the bottom of the page. Okay. So the pin is shown at the bottom of the page, 980815. Okay. So you have this situation, and I want you to answer. Rank the magnitude of the electric field at points A, B, and C as shown in the figure. Greatest magnitude first. So 20 seconds. So make your decision, then I will start the Kahoot. Everybody joined? Ready? Who's not ready? Okay. Give you time. Okay, so let's go because we want to finish the material today, hopefully. Okay, so you will have 20 seconds to enter your answer. Choose between A, B, C, or or D. Okay, go ahead. You will have 20 seconds. Another 20 seconds. Please, everybody participate, even if you do not know the answer. I need this for attendance. Okay, excellent. We have 15 correct answers, and we have 14 incorrect. Well, almost split. All right. All right. So let's look at this. What did we say about electric field lines? We said the electric field lines, the density or the number of lines per unit area indicates the strength of the electric field. So by just visually looking at this, you can clearly see that at point C, the electric field line here, if this is a Q and a Q, electric field lines will be 0 here. The electric field is 0, so that's why we are not drawing any electric field lines. Okay, point A is closer to the charge Q. Okay, and that's why if you count the number of lines per unit area, if you draw an area like this and you count the number of lines, you will find that these are much more than the number of lines per unit area at point B. So the highest is going to be EA, is going to be the highest. So here EA is higher than EB, is higher than EC. In fact, if the charges are equal, the electric field right at the middle between them is going to be 0, because one will be the left charge will cause an electric field pointing away, the right charge will be causing an electric field like this, and they will cancel each other right at the center between them. Okay, they will not cancel here, because if you take here, this is one electric field line and this is here the other electric field line, they will have a component that is in the y direction. So they will only cancel at one point, which is right between the two charges along the line joining them. Clear? واضح? Any questions? Okay. All right, so let's move to the next topic, and I don't know why the computer is slow today. Okay. All right, so here, this is a motion of charged particle in uniform electric field. Okay, uniform, what do you mean? Uniform meaning the same magnitude and same direction everywhere. So if you have two plates, and we will study this in the future, if you have two charged plates and you establish a voltage between them, let's say 20 volts or whatever the voltage, between those two parallel plates, the electric field is going to be uniform, meaning it's always pointing away from the positive plate towards the negative plate, like it's seen here. And if you measure the electric field at any point, it will be the same, because it's uniform between the two charged plates. Okay? If you place a charge Q in this electric field, it will experience a force F, and the force F is just given by QE. So hence, it's a constant force. So the charge will be experiencing a constant force, and we can use the equations of motion at constant force. Constant force meaning we have a constant acceleration. Okay? Notice in this case we ignore the gravitational force because it's very insignificant, very small compared to the electrostatic force. So we will assume that the charge is only influenced by the electrostatic force. So this is the force that is applied on the charge. Obviously, if it starts with a velocity v0 here, it can start at rest. It will reach higher velocity here, v final will be higher because there is a constant force and the charge has a mass also, m. We can write the equations of motion for constant acceleration. Let me remind you. So if we have, this is the x direction, we can write that first of all, x is equal x0 plus v0t plus 1/2 at squared, and we can write v is equal v0 plus at, and we can write v final squared minus v initial squared is equal to a delta x. These are equations of motion. These are equations of motion for f being constant. Okay? If the force is not constant, you cannot apply these equations. Clear? Okay? So if you take the case, for example, of a point charge, okay, the electric field is not uniform. It gets stronger as you get closer to the charge. So the force is not going to be constant. So let's assume this is a positive charge, and you bring close to it a test charge that is Q0. It will experience a force, but this force, as the charges are getting closer together, it will vary, it will increase. So in this case, the force, oops, I can't believe this. Shoot. I lost my pen again. All right, so it's okay. Okay, so okay. So we were explaining that in this case we can write Newton's law. The sum of the forces is equal to ma, and since we have only electrostatic force, the electrostatic force is equal Q times E. Okay, Q times E. Okay, so we can write that the acceleration vector in this case is just equal Q times the electric field vector divided by the mass of the charge. All right. So this is the same illustration or same example. Here we have a uniform electric field. It's indicated by the electric field lines. These are the black lines that are shown here. Okay. And if you place a positive charge in this uniform magnetic field, it will experience a force in the same direction as the electric field. We said if it's a positive charge, the electric field and the force are in the same direction. However, if you place a negative charge, it will experience a force in the opposite direction of the electric field. So if the charge is negative, the force that it experiences is in the opposite direction as the electric field. We have already explained this. So an electric field, if the charge is positive, the force has the same direction as the electric field. In an electric field, if the charge is negative, the force has the opposite direction of the electric field. Please remember this, so that when you solve a problem, use the equations to get the magnitude, but when you're asked about the direction, use the reasoning. Use your reasoning to determine the direction. All right? So let me go back to this question. Okay? Let's assume we have an electric field as shown with a green arrow here, and we want to determine the direction of the force in this case. So the charge is an electron. So is the charge to the left, to the right, up or down? Anybody? Yes? To the left. So because it's a negative charge, we said if it's a negative charge, the force is opposite to the direction of the electric field. Okay? Unfortunately, my pen is not well, but let me use my mouse. Yeah, I can only use my mouse. So if the mouse, so the force will be in the opposite direction of the electric field. Okay. Now, let's take the second situation. The electron initially is moving along the y-axis. What is the direction of the acceleration? So notice the velocity is along the y-axis, so it has an initial velocity in the y-axis. What do you think is the acceleration? Is the acceleration to the left, to the right, up or down? Okay, so we have up here. Anybody else up? Okay, anybody else up? Who says something else? Anybody says something else? Okay, let me ask, why did you say, remind me of your name, please. Ibrahim. Why do you think the acceleration is up? And I said it's moving at a velocity. It's a constant velocity. Well, if it's we in physics 121, we never said that the direction of movement is the direction of acceleration. In fact, if we have a constant velocity, if v is constant, the acceleration is 0. So this is a constant velocity. I did not say it's moving faster or slower. It's a constant velocity. Constant velocity, we said, meaning the acceleration up is 0. There is no acceleration on the y-axis. So what is the acceleration? Yes. To the left. Why? Newton's second law. Thank you. What's your name, please? Halima. Thank you, Halima. We have a force equal to ma. Newton's law says the sum of the forces is equal to ma. Here we have only one force, which is the electrostatic force. Okay, and we have said the force is to the left because it's opposed to the electric field. Since the force is to the left, the acceleration has to be also to the left, because F is equal to ma. It's a vector equation. Okay. Okay, so F is equal to ma. You can draw the vector line, the symbol on F and the vector symbol on A. So the acceleration is always in the same direction as the net force that is working, that is applied on this mass. All right, so let's do the Kahoot again and answer this question. I thought we have Kahoot playing. Okay, so do not exit. So let's see. Look, so these are the scores. All right, this is the next question. So I want you to answer for the case to the right. This one here. The electron initially is moving along the positive x-axis. So there is a positive axis. How does its velocity change? Does it decrease, increase, or stay the same? Please use Kahoot. And so you have A, the velocity decreases, B increases, and C, it stays the same. It's the same Kahoot, same number. Okay. Can I start it? Can I start it? Everybody is logged into the Kahoot? Okay, so let me start it. 20 seconds to enter your answers. I hope everybody gets it right this time. Okay, well, so 16 are correct, and we have 11 are incorrect. Still, so let's go back. You can see here, so this is a velocity. The electron has an initial velocity, but the electric field is to the right, so there must be a force to the left. If the force is to the left, the acceleration is to the left or to the right? The acceleration is to the left. If the acceleration is opposite to the direction of the velocity, will the velocity increase or decrease? It will decrease. So the force is a retarding force. It's opposed to the direction of the velocity. So the electron is running fast, okay, or moving fast. The force is pushing it backwards, so it's slowing down. So it will reach 0, and then it will start going backwards. Okay, clear? I hope this is clear. So remember, Newton's law is very important in all. Whenever we speak about forces, you have to be able to recall Newton's law. All right, so let's. These are the answers. The force to the left, the acceleration is to the left, and the velocity decreases if the electric field is pointing to the right. All right. So here I don't have the pen. So we have the uniform electric field, and again we have a charge, okay, starts at to the left with zero velocity, okay, and the charge is q, the mass of the charge is m, okay, and the question is what is find the particle velocity when it reaches point B, okay, so positive and negative charge. So while you're thinking about it, let me go to the whiteboard. Sorry for the students I'm recording for. Okay. Everybody can see. So, this is just a simple problem with the motion of so we have a positive plate and a negative plate, and we have a charge Q that has an initial velocity V0. Image is V0 is equal to 0. Okay, and this distance let's call it D. Okay, and we want to determine the velocity when the charge reaches this point. So obviously the electric field lines are like this, they are indicated there, so this is the electric field. Okay, now this charge is positive, so the force is going to be like this, F. This is the electrostatic force. We ignore gravitational force because we said it's really insignificant. So what we can write the electric force is just equal to times E. And we said the force is equal to times E. And we can use Newton's law. This force is equal to M times A. The mass times the acceleration. That's why I'm using magnitudes here. So I can get the acceleration here. It's just QE divided by M. Acceleration is QE. Now this is a constant force because we said this is a uniform electric field. So we can use equations of motion with constant acceleration, constant force, and the equation of motion. They ask for the velocity. So I can use v squared, v final squared, minus v0 squared, which is 0, this is 0, is equal, so 2a, but here 2a times delta x, which is t in this case. Delta x is t. Okay? So I can replace a and I can solve for t. Let's find the speed. He wants the speed. So v final is just square root of 2a times t, which is square root of 2. I replace a by qe divided by m times t. This is the velocity. This is one way. The other way I can solve this problem is by using the conservation of energy. Okay? What do we have? We have the equation of conservation of energy, that the work done by external force, let's assume in this case the electric field is an external force, okay, is equal to the sum of delta K, the change in kinetic energy, plus the change in potential energy, and so on. So here we have, let's assume we have only the kinetic energy. The force, the work done by the force, so we remember, work done by a force is just equal to force times the displacement. Or to be more accurate, it's F dot D. But since F and D are in the same direction, this work is going to be just Ft. So I can write Ft is equal K final minus K initial. K final is 1/2 M V final squared minus 0, because V initial is 0, minus 0. So I can solve for V final. It's just equal. So F is equal to QE. Yeah? So let me replace this. So this is going to be equal to QE minus T. And I can solve for V final. So V final is going to be 2 QED divided by M squared. So I use either Newton's law and the equation of motion at constant acceleration, and the second way is use conservation of energy, the work done, or you can say the work kinetic energy theory. work kinetic energy theorem says if you have a particle, not a system, or you have an object, the work is equal to the change in kinetic energy. W is delta K. This is what we call the work kinetic energy theorem in physics 120. Okay. Unfortunately, we cannot explain this for the recording, but all right. So, okay. So sorry here for the students who could not hear me. I was explaining this on the board, but we just used the force is equal to ma, which is equal to QE, and we solve for the acceleration. In this case, it's equal to QE divided by m. And since its equation, this is motion with the constant acceleration and constant force, we can use the equations of motion. In this case, V final squared is equal to V initial squared plus 2 x minus x initial, which is d. So we can solve for V final, which is square root of 2QEd divided by m. Or we can use the work kinetic energy theorem. The work is equal to delta K, and the work is the force times the displacement. And delta K is K final minus K initial, which is 1/2 mV final squared, and we find the same equation. V final is square root of 2QE d divided by m. Okay, all right, I still have 4 minutes. Okay, now let's assume we have a situation like this. In this case, we have an inkjet printer. Okay, the ink drop is generated here, and it goes through a charging unit. It charges this drop, and it's a negative charge. Then it goes through deflecting plates. The deflecting plates are controlled by the printer, the signal that it gets. Okay, so let's assume it's establishing an electric field from the positive to the negative plate. So the charge is negative, so the force on this negative charge is going to be opposite to the electric field, so it's upward. It's an upward force. That's why this drop will deflect in the upward direction. So you can see here, this is deflecting in the upward direction. Okay, so the signal from the computer negatively charges the ink drop, which is deflected by the downward directed electric field set up between the deflecting plates. Okay, so this is the paper here. When the ink drops on the paper, it will make a mark, a permanent mark on the paper. Okay, and the question is, if we want to determine how much is this deflection. So now we have motion in the x direction. Is it a constant velocity or it's changing velocity in the x direction? It's constant velocity because there are no forces acting on the particle in the x direction. The force is only vertical. It's upward force. How about the motion in the y direction? What is the motion in the vertical direction? How can we describe it? It's motion with constant acceleration, because there is a force, which is electrostatic force. It's equal to QE. This force is equal to ma according to Newton's law. Okay, so we have equation of motion at constant acceleration, but in this case the acceleration is upward, and we can solve. So we have the direction of motion in the x direction and motion in the y direction. Remember, projectile motion, we have x direction and y direction, and we can solve this. So let me quickly, I don't have time, I have only 1 minute left, so I'll go to the solution, and sorry for that. Okay, so the equation of motion in the y direction is we have zero initial, we're assuming zero initial velocity. So here the mass is m, charge is q, of the drop is minus 1.5 10 to the minus 13. It's no, it has initial velocity in the x direction, but there is no initial velocity in the y direction. Vy is zero, initial zero. The length is 1.6 centimeter. The electric field is 1.4 10 to the power 6. So we can use the acceleration is equal to the force divided by the mass, and the force is equal to QE, so we can get the acceleration. Okay, and we need to determine t. So I have the acceleration, but I need to determine t. How can I determine t? We have a constant velocity in the x direction, so the distance that is traveled divided by the time is equal to the velocity. So I can get the time, which is L divided by V, and I can replace in the equation of y and we can solve for y. So y is equal 1/2 QE over m times L over V squared, all of it, the L of V, and we get 0.64 millimeters. So this is a projectile motion, electric field, Newton's law. So we're applying a number of principles. Projectile motion, motion in the x direction, constant velocity, motion in the y direction, constant acceleration, and we're applying F is equal to QE, and we're applying Newton's law, F is equal to MA. So we are applying three very important concepts on physics. Sorry for taking a little bit longer, and so tomorrow, hopefully we'll do some problems and start. We're supposed to finish chapter 23 this week, but we are late. Okay, so we'll see you tomorrow, inshallah.